All right, we resume with a discussion of standard state, another important idea that relates to enthalpy, a big part of 5.3 throughout this chapter. And I apologize, I think once or twice in the previous videos I did refer to it as chapter 15. Your other two partner chemistry courses are both in chapter 15, hence the confusion, lots of fives right now. Anyway, getting to standard state. When we are calculating enthalpy changes at delta H that we referred to before, usually, not always, but usually we're thinking about a system where the reactants and the products are in the same condition as one another. Okay? So a standard state, and we choose the definition of a standard state, right? It's an accepted set of conditions to give us a reference point for a determination of properties when we then change those conditions and go somewhere else. So the IUPAC standard state conditions, remember IUPAC, we had that abbreviation when we learned nomenclature, International Union of Pure and Applied Chemistry. It tells us that we're working with a pressure of 1 bar, 1 atmosphere. And if we have solutions, they're at a 1 molar concentration. Remember that capital M represents molarity, moles over liters. So how does this tie into enthalpy? If we are reporting an enthalpy change under the IUPAC standard state conditions, right, then we give it that superscript not. You see that appearing right here, but this is the symbol we're looking for right there. That delta H not tells you that we're under standard state conditions. But notice we didn't refer to temperature when I was defining standard state. Okay, the usual temperature we're working with is 298 Kelvin, or 25 degrees Celsius, just slightly warmer than room temperature. And if we're working at that temperature, which 9 times out of 10 we will be, we state that with a subscript 298. Okay, so delta H, enthalpy change, not standard state, temperature 298 Kelvin. Whole bunch of symbols to tell you exactly how that enthalpy change is occurring. And it's important to state all those things because you can provide information about an enthalpy change. In your textbook, if you look at the back of Openstax, has a lot of information about those enthalpy changes. Okay? But keep in mind, we saw this at the end of the previous video, right? Delta H is extensive. It does depend on the amount of substances present. Okay? So if I double the amount that's present, I double the overall enthalpy change. So when we are reporting these things, and that's what the previous practice problem kind of did, we report enthalpy changes on a per mole basis. That gives us what's known as a standard enthalpy of combustion, and then later a standard enthalpy of formation. And a standard enthalpy of combustion, notice the subscript C over here, right? That's telling us combustion. That's the enthalpy change when exactly 1 mole, okay, so we've now normalized it, and the not tells us we're still at standard state, exactly 1 mole of a substance burns. Okay. We call that the heat of combustion. Gives us some information that we can work with later on. Okay. Here we have an example for the heat of combustion of ethanol. If I look at the bottom, I have a balanced chemical equation. Okay. It's when exactly 1 mole, no more, no less, exactly 1 mole of ethanol reacts with 3 moles of oxygen to produce CO2 and H2O. You might remember from chapter 4, those are the products of a combustion reaction. Okay? Sub 298 tells me I've been working at a temperature of 298 Kelvin, shown here as 25 degrees Celsius, and 1 atmosphere of pressure. Okay? All things that are important, all factors that go into determining that final value of negative 1,366.8 kilojoules. Okay, that is the standard enthalpy of combustion, or the heat of combustion of ethanol, the thing that there's 1 mole of on the reactant side. And that can give us a lot of information. Here we see other heats of combustion for carbon, hydrogen, magnesium, sulfur, carbon monoxide. And now the question is, where is this useful? Well, how about the enthalpy of formation? Thinking about the standard enthalpy of formation, or heat of formation, 2 terms that mean the same thing. Notice we have a subscript F now, enthalpy of formation. Well, that's the enthalpy change for a reaction where exactly 1 mole of something is, you probably guessed it, formed, right? Heat of formation, exactly 1 mole formed. Heat of combustion, exactly 1 mole combusted. So if we look down here, right, the heat of formation, right, delta H, change in enthalpy, not standard state, sub F, heat of formation of CO2, negative 393.5 kilojoules per mole. Okay? In that reaction, right, forming 1 mole of CO2, it's not just forming 1 mole of CO2 from anything, right? It's forming 1 mole of CO2. This is a key line right here. 1 mole of CO2 from its constituent free elements, so the elements that make up CO2 in their most stable states at standard conditions. So if I think about CO2, I break it up. It's got C, it's got O, carbon and oxygen. Okay. What's the most stable form of carbon? It's a solid with 1 mole, just single C, right? What's the most stable form of oxygen at standard state? Right? Remember, oxygen's a diatomic, okay, so it's O2 is its most stable form, and it's a gas. Its most stable state at STP. Okay? So the heat of formation of CO2 comes from 1C, right here. What's oxygen? O2. All right, easy, balanced chemical equation. Now, an important idea where we're going with Hess's law, and I've got another set at the end that'll remind you of this, the standard enthalpy of formation of an element, so anything that's elemental in its most stable form, is equal to 0. And that's an important idea because that, once I have these enthalpies of formation, allows me to predict the enthalpy changes for a chemical reaction using the species that are involved. So a practice here, there's 2 of them, writing the heat of formation, so delta H F naught, right, heat of formation reaction equations for ethanol in A and calcium phosphate in B. So the strategy to solve these, identify everything that's a part of those molecules. So in ethanol, I have carbon, I have hydrogen, I have oxygen. And in calcium phosphate, B, I have calcium, I have phosphorus, and I have oxygen. So those things will be your reactants. Then you're tasked with assigning them their most standard state, solid, liquid, or gas, keeping in mind anything that might be diatomic, and then balance the reaction. So pause the video now, give those a shot, and then we've got the answer on the next slide. Answer shown here. Okay, top for ethanol, bottom for calcium phosphate. All right, I split ethanol into carbon, hydrogen, and oxygen. Okay, the most stable form of carbon is solid, and there are multiple solid forms of carbon, right? Diamond's another one, but when we're reporting standard states, we're considering graphite. That's above any information you'd be expected to know on a quiz. Okay, we have hydrogen, which is a gas in its most stable form and a diatomic. And then O2, right? Oxygen, as we just mentioned before, diatomic, gas. And to balance it, right, notice I've got 2 carbon, 3 H2s, and a half O2. Because remember, these are thermochemical equations. I can get away with non-integer coefficients, and I have to because by definition, the heat of formation reaction forms exactly 1 mole of ethanol. If I were to make that a 1 instead of a 1/2, I'd have to make 2 moles of ethanol. That's no longer a heat of formation equation. When you're writing a delta HF, you're always making exactly 1 mole of your product. Okay. Same thing on the bottom, calcium, phosphorus, and oxygen. The only tricky thing would be remembering from chapter 1 that phosphorus, right, P4 is the most stable form. So that could be tricky, right? Just like the diatomics, phosphorus likes to be P4, sulfur likes to be S8. And that finally brings us to Hess's law, which is arguably the largest part of chapter 5. Okay. Hess's law in the calorimetry problems, Q equals MC delta T, 2 huge ideas that are certain to be on a quiz or a test. And Hess's law gives us 2 ways to determine the amount of heat involved in a chemical change. Okay. And I'm actually getting ahead of myself. There are 2 ways to do Hess's law. We'll get to those in turn, but that's not what this slide is referring to. The top of this slide is telling us that, okay, there's 2 ways to determine the heat in any reaction that you're thinking about. One is measured experimentally. That's what calorimetry is, right? Q equals MC delta T. But Hess's law is this second part. Calculate it from enthalpy information we already have. And that's important a lot of the time because some reactions are too violent to actually do calorimetry with. Okay? Other ones are impossible to get the reactants that you want to come together. Okay? So where we can't measure it experimentally, we can calculate the heat that's involved in a chemical reaction with Hess's law. And that's my favorite part of chapter 5 and one of my favorite ideas from the course as a whole, because you can always be sure that you did it correctly. Okay. So Hess's law, definition. If a process can be written as the sum of several stepwise processes, then the enthalpy change of all of those steps together equals the sum of the enthalpy change of the individual steps. Right? So thinking about state functions again, if I'm trying to go up a floor, my final altitude change is the sum of all the steps I did walking up a staircase. That's what Hess's law is all about, right? And we can do that. It doesn't matter how we got there. It's a state function, just depending on where we started and where we finished, not how we got there. And as I mentioned just before, 2 ways to do Hess's law. Okay. Here I'm thinking about the heat of formation of CO2. Okay, we saw that before. Carbon and oxygen coming together to form CO2. Delta H is equal to negative 394 kilojoules. But let's assume that I was looking at this reaction and I didn't know the value of delta H. Okay. But I did know the enthalpy value for the formation of carbon monoxide, CO, from carbon and oxygen, and then the formation of carbon dioxide from carbon monoxide, NO2. 2 individual reactions. If I add those 2 reactions up, just like if you were doing redox or balancing a net ionic equation, right? Adding together all the reactants and the products, okay, combining any like things, eliminating things that appear on both sides, right? My overall net reaction, carbon plus oxygen, goes to CO2. And that's exactly the reaction that I was considering before. So if I have 2 steps that can be added together like this, these 2, right? If the reactions can add together to give me the reaction I'm concerned with, then I can add the enthalpy values together. And the sum of those enthalpy values is equal to the enthalpy change for your net reaction. That's what's shown here. And sure enough, negative 111 plus negative 283 is equal to negative 394, which we already knew was the heat of the reaction for carbon and O2 coming together to form CO2. That's the power of Hess's law. Delta H, your enthalpy change for an overall reaction, is the same if it's just 1 big step, 2 individual steps, 20 steps that you add all together. You can still get the enthalpy change for an overall reaction, right? Our negative 394 that we saw first, and then adding 2 individual steps, 111 and 283, right? It's just like a roller coaster. You start and you finish at the loading bay, right? You can do a whole bunch of turns and curves and everything else, right? But you start and finish at the same place. And that's what Hess's law is all about. Okay. But a couple of things to keep in mind. This was introduced in the previous video for chapter 5, right? An enthalpy change is directly proportional to quantities of reactants or products. Okay? So the enthalpy change that's given to you is for the reaction exactly as it's written. If you multiply or divide all of your coefficients, you have to do the same to the value for the enthalpy change. And I can flip a reaction as well. If I flip the reaction, right, I make the reactants products and I make the products reactants. I can do that, but if I flip the reaction, I flip the sign. And keeping those 2 things in mind, you can take a reaction and manipulate it however you want. This is what a Hess's law problem looks like. This asks you the standard enthalpy change for aluminum and chlorine coming together to form aluminum chloride. But I'm not given that delta H over here, right? I'm given these reactions in here. This is my toolbox. I have to figure out a way to put these reactions together, get all the reactants and products to cancel each other out so that at the end of the day, I'm left with just this reaction. However I manipulated these equations, okay, if I flip them, if I multiply them, anything else, I do the same thing to those enthalpy values, and I need to get them to add up to be to that reaction on the top. Then when I've worked all my equations, the right way so that they cancel out to make this chemical equation, all I have to do is add the enthalpy values, okay, and I may have changed these to get there. That's equal to the enthalpy change for the overall reaction. And as with all the other extended response problems, I'll upload a separate video showing how to do that. But one other note that I'll put on your radar, okay, sometimes in this toolbox of reactions down here, you're given more information than you actually need. Okay, so here we have 4 reactions to work with. I know I'm going to need at least some of them to add up to get that reaction to the top. Sometimes you're given more reactions than you need. You know, I could have written a 5th, 6th, 7th reaction down there. You don't always have to use all of them, so don't panic there. But you do 100% need to practice these HESS'S law type problems. Okay, they are a fundamental idea from chapter 5. How else can we do HESS'S law? Okay, we can apply HESS'S law to get the enthalpy change for a reaction using enthalpies of formation of the reactants and products, those delta HFs we talked about at the beginning of this video. And those stepwise reactions, right, the reason we can add those together is because really what we're doing is thinking about all the reactants that we have, those molecules, kind of breaking apart into their individual atoms, right? Think about that like Thanos with the snap, right? Everybody just kind of dissolving into individual reactant atoms. But then they come together again to form, right? They recombine. That's what point 2 down here is saying. Right? They come back together to form the products. So if I think about the heat of formation of the reactants, okay, those things are kind of disappearing. So it's the opposite of formation. So I use the negative heat of formation. And then I think about the heat of formation of the products. Okay? So this second application of HESS'S law is just breaking things down, building them back up. So that tells us that I can take the sum of the standard enthalpies of formation of the products, the things that are being formed, so just the normal values, okay, plus the sum of the negative values of the heat of formation of the reactants, because those are the things that are breaking apart. And that turns into this reaction, right, sorry, not this reaction, this equation right here. The heat of a reaction, the standard heat of a reaction, delta H naught reaction, is equal to the sum of the heats of formation of the products multiplied by n, their stoichiometric coefficient, minus the sum of the heat of formation of the reactants, and I'm not sure what happened to that text on this slide, again multiplied by their stoichiometric coefficients. So looking at this problem here, you see this, a whole bunch of reactions given to you or a whole bunch of delta H values given to you. Those are both HESS'S law type problems. Okay. So now in this equation, this question, and again, I'll upload a video showing how this one is solved, right? I'm tasked with using these enthalpies of formation, products minus reactants multiplied by their stoichiometric coefficient. That gives me the delta H value for this reaction. 2 different ways of doing HESS'S law. And the answer to this one, okay, if this slide wants to proceed, yep, there it is shown in the slides, right? Negative 138.4 kilojoules. And because delta H is negative, I again know that this is an exothermic reaction. One last note, I alluded to this earlier in the video, right? If you're asked to do HESS'S law the way that problem just asked, okay, those heats of formation have to be given to you. I would never ask you to memorize them. So if something isn't given to you, that means that it's probably something in its most standard state. Okay? We referred to this before. If something's elemental in its standard state, that heat of formation is 0. Okay, so the delta HF of O2 is 0. The delta HF of solid sodium is 0. So keep that in mind when you're solving these types of problems. At the end of our chapter 5 slides here, there are 2 review problems, 2 additional applications of HESS'S law. This is the first one, first application of HESS'S law, manipulating equations to find the delta H value for this problem. And then the second application of HESS'S law, heats of formation of the products minus the heats of formation of the reactants multiplied by their stoichiometric coefficients. Okay, I'm not going to upload videos for these 2 slides. I'm going to ask you to solve them on your own. We'll go over those in the review session for those of you that are participating. If you don't have time there, you can try and solve it. Send me an email. I'll tell you if you did it correctly or not. But if you want the extra practice, which I strongly recommend you should, these would be the best way to do that. Know how to do HESS'S law, know how to do calorimetry, Q equals MC delta T, know the various definitions that came from chapter 5. Okay? All important ideas. Make sure you read over the textbook. Okay, all of chapter 5, you've got sapling, you've got a couple of lecture videos to help out. Okay, there are other resources on YouTube, Blackboard discussion with your peers. Okay, feel free to discuss the problems that are in here or anything else on sapling. Okay, and as always, contact me with any questions.